6 on polynomial congruences 1. We gave an introduction to this. We kind of set up the last time we set up the grand kind of scheme of attempting to solve polynomial congruences. Problems like this, where f is a polynomial with integer coefficients, and trying to identify that given some modulus n, trying to identify what the solutions are to f of x being congruent to 0 modulo n. Now, what exactly we mean by finding the solutions of that, we spent some time talking about that, and we arrived at the description that, okay, so these objects x that are going in here are certainly integers, but rather we should think of them as being congruence classes modulo n, okay? Because if you've got a congruence class modulo m, whichever integer from that one congruence class you stick into f of x, all the values you get out, while they'll be different, they'll all be congruent to one another modulo n. So if one integer x is a solution of this, so is any other integer x which is congruent to any other integer congruent to x modulo n. Okay? So the solutions that we're looking for are the congruence classes. So you think of a whole congruence class modulo m as either satisfying this or not. Okay? And then, now we all know about what the story is with polynomial equations, say applied to the complex numbers. When a polynomial has degree n, the polynomial has exactly n complex roots. You have to count them with multiplicity, so you can have roots with multiplicity greater than 1, but it'll have exactly n roots. So that's kind of very nice connection between the degree of the polynomial and the number of solutions it has. We looked at a couple of examples which showed that there can't possibly be any such a nice clean story for polynomial congruences over the integers, because we looked at a linear congruence, a degree 1 polynomial, 2x minus 3, congruent to 0 modulo 4, and we found that that had no solutions at all. And then indeed, at the other extreme end of the scale, we looked at something of degree 2, x squared minus 1, congruent to 0 modulo 8. And just by simply investigating the 8 different congruence classes, we observed that you've got 4 solutions to that. 4 different congruence classes, modulo 8, which are solutions to that polynomial. So sometimes a polynomial will have no solutions at all. And there are situations, there's at least one situation, but infinite number of situations where you've got a polynomial with more solutions than its degree. So there isn't such a nice clean connection between the degree of a polynomial and the number of solutions it has. Now that's not to say that there's no connection at all, but it's obviously much more complicated than just the number of solutions equals the degree. So in this chapter and in the next, chapter 7, we'll be coming to an understanding of this whole general problem. So by the end of the chapter 7, we'll fully understand this kind of situation. And we'll have at our hands a method, an algorithm for obtaining the solutions of this. Okay? Given any polynomial f with integer coefficients and any modulus n. Okay. So what's in this first chapter? Well, in this first chapter, there's 2 things. There's the treatment of linear congruences. So linear congruences are where the polynomials have degree 1. So linear congruences means degree 1 polynomials. So things like the 2x minus 3, or in general, it's going to be ax congruent to b. So just an x term and a constant term, b. And we'll be able to, and there's a full description here in a couple of pages of what the story is for those. How to solve those, when they have solutions, when they don't, and also how to see exactly how many different solutions they have. Of course, when we say that, we mean how many different congruence classes modulo n provide solutions for them. So we're going to work through these results about linear congruences now. So this is just an application of what we know about congruences already. But there's a key couple of results which we're going to be calling on. So I just put these up on the whiteboard just so we can have them in front of ourselves, so we can see. So recall from chapter 4, these results about cancelling factors in congruences. Cancelling factors in congruences. So there was a theorem, theorem 4.3. And this basically said that if you had an x times c congruent to a y times c modulo something, modulo an m. So here you can see that there's a common factor in the two things either side of the congruent sign. So what you want to do is just eliminate the c. Well, you can eliminate the c. That's true if let's be just careful. Let's just say implies. This does indeed imply that x is congruent to y modulo, but not necessarily modulo m over d, where the integer d is the greatest common divisor of c and m. Okay, so you can get rid of the c, but you have to tweak the modulus. Okay. So a special case of this, which we want to remind ourselves, special case was when d equals 1. So when the GCD of this c and this m is 1, then you can say that x is congruent to y modulo m over 1. So it's still modulo m. So this was xc congruent to yc mod m. If the c is co-prime to m, that just implies that x is congruent to y modulo m. Is there a way to explain why that's true? Good question. Explain why that's true. What is it about when c is congruent to m? What's a significant fact that comes from that? If c is congruent to m, then something important about c to do with the modulus m. No, because then the greatest common divisor won't be 1, it'll be m. It's to do with the operation of multiplication. When c is co-prime to m, then C has a multiplicative inverse, modulo m. That's it, yeah. So when c is co-prime to m, then it has a multiplicative modulus, a multiplicative inverse modulo m. So there is a number, there is another congruence class. Maybe it's c itself, and one of the other congruence classes modulo m. That's equal to c inverse. So you just multiply both sides by c inverse, and that gets rid of the c. So you're just left with x congruent to y. Okay. So you can always multiply both sides of a congruence by anything, and the congruence will still be true. Okay. So the reason for this is, or you can explain this since c inverse modulo m exists. So you can hit both sides with it. So if we're looking at linear congruences, we're going to want to call upon this. And just another slight variant on it is theorem 4.4. And that says that if you have x being congruent to y modulo m, this will be equivalent to, you can always just multiply all three parts of the congruence, the numbers x and y and the modulus. You can multiply them all by the same factor c, and the congruence is true. Or going the other way, if you see a common factor in the x
in the two things either side of the congruence and in the modulus itself, you can cancel that common factor and reduce the whole modulus. Okay. So these are some important results about cancelling factors, and these are the main tools that give us these results about linear congruences in this chapter 6. Okay, so I need somewhere to stand where I'm not in the way of all of that. So so let's have a look. So first of all, so we just agree a linear congruence is something of the form AX being congruent to B modulo n. And so theorem 6.1 looks at a special case. So this special case is when the coefficient of x, is co-prime to the modulus. So from what we've just been recalling there, when a is co-prime to n, that means there is an inverse to a, right? So if you're faced with this equation, ax congruent to b, and you're looking to solve it or to see whether there's a solution x, well, there is, because you can, in effect, cancel the a from the left-hand side. Well, you more appropriate talk is you say you multiply both sides by a inverse. So then you'd be just left with x on the left-hand side and a inverse times b on the right-hand side. But you can only do that if a inverse exists. If there is a congruence class called a inverse, which you can use to multiply both sides. If the a inverse doesn't exist, then you can't do that, obviously. So such a thing will have a unique solution. There'll be a unique congruence class. It will be the congruence class represented by a inverse times b. Now, the way we represent a inverse here is a to the power of the Euler-Tauschen function value, phi of n minus 1. Okay. That's another thing. If the GCD of two numbers a and n is 1, then a inverse is going to be congruent to a to the power of phi of n minus 1 modulo n. So the inverse to a will exist, and you can we can represent it as a certain power of a, as a positive power of a. So we know how to calculate the inverse of a, or calculate a representative of the congruence class, which is the inverse of a, using the Euler-Tauschen function value. So that's really the proof of theorem 6.1. If you're looking at a linear congruence where the coefficient of x is co-prime to the modulus, then straight away there's one unique solution. So there is a solution, and it's unique. A unique congruence class. Of course, there'll be an infinite number of integers x which solve this congruence, because anything congruent modulo m to this integer will solve it. Okay, but there's just the one congruence class. So I think that's more or less what I say in the proof of it there. Just that GCD of a n is 1, so the inverse exists, so you can multiply both sides. So is that okay? Any queries on that, or things I can clarify? Okay. So that special case of linear congruences is, we've got a complete understanding of that. If a is co-prime to n, there is a solution, it's unique, and here's a way to calculate a representative of the congruence class. Okay, all aspects of the problem then are clear, are known to us now. Okay, but that's just a special case. It's just a special case where a is co-prime to n. Now that's moderately special behavior. There's certainly plenty of situations where you can have an ax congruent to b, where the a will not be co-prime to n. Okay? So what about those situations? So that's what we look at next. So we've the treatment of that situation. So that's the general situation where we allow a and n to have any number as a greatest common divisor. Not the special case where it's 1, but just to be able to capture any case. Now the treatment of this we split up into two cases. So first, in theorem 6.2, we prove a criteria for the existence of solutions. So we say that there are solutions to this if and only if some condition. And the condition is nice and simple. If and only if this greatest common divisor d divides the constant term b. Okay. But now this result tells you when there are solutions and when there aren't solutions. What it doesn't tell you is how many solutions there are. And it also doesn't tell you, well, at least in the statement of the result, it's not telling you how to go about finding one of the solutions. So it's just an existence proof. It says, well, if this is true, if D divides B is true, there are solutions out there. If D does not divide B, then there aren't solutions. But there's nothing in the statement of the result which gives you instructions about how to find the solution, which is very different from the statement of the result up here, which actually gives you, in effect, a formula for the solution. So theorem 6.2 is just the existence result. Then the next theorem, 6.3, looks at the situation where there are solutions, so where D does divide B, and then it gives a recipe for finding the solutions. And it tells you exactly how many solutions there are. There will be D solutions, exactly D solutions, where D is this greatest common divisor of A and N. Okay? So we'll look through the proof of these two results, and then I think then there's a bunch of examples to look at, which we'll try and get to in this hour, but if not, we can work through lots of those tomorrow. So first, the existence argument. So it's an if and only if statement, okay? So for the most part, we prove if and only if statements by taking the two directions separately, okay? So which one do we do first? So first of all, we're going to assume that there is a solution. So I'm going to assume that AX is congruent to B. So I'm assuming the existence of at least one integer X which satisfies this congruence. Okay. So it's clear what I'm trying to do. I'm assuming this part, so that means I'm trying to prove, in this half, I'm trying to prove that D divides B. Okay. Maybe I should have done this out on paper without reading it, but yeah. So we're trying to prove that D divides B. So the way we can do that is to get some expression for B, to get an expression for B which is clearly divisible by D. Okay. So that's what we aim to do. So starting with our assumption, if AX is congruent to B, you see the way we're working, straight away we just unravel the meaning of this. What does this statement actually mean? You think about what congruence means. This thing, the thing on the left is congruent to the thing on the right. What that means is that n, the modulus, divides the difference between them. Okay? That was the definition of the congruence relation. Okay? So n divides the difference AX minus B. Well, then what does that mean? What does this division relation mean? N divides a number. What that means is that the number is equal to some integer multiple of n. So there exists some q out there somewhere, some integer q, such that AX minus B is equal to q times n. Now there's an equation with a B sitting in it. Okay, so we simply reorganize it. So it's B equal to AX minus q times n. Now what is it about that equation? How do we kind of characterize it? Think about it. Well, it's a linear combination of A and N. Okay? A and N are the other two ingredients of the problem, part and B. So we've got something quite significant here. If there is a solution, X, the consequence is that B is a linear combination of A and N. Okay? The X is the thing multiplying the A, and this Q, quotient value, is, or negative Q, is the thing multiplying the N. Now, a key fact about linear combinations of pairs of numbers. What's the key fact about those, which is related to the greatest common divisors? Okay, so this is going back all the way to chapter 2. Every linear combination of two numbers, it'll always be divisible by the greatest common divisor. Indeed, it'll be divisible by any common divisor. Okay. So because B is a linear combination of A and N, any common divisor of A and N now must divide B. because the common divisor will divide this term because it's dividing A, and it will divide this term because it's dividing A. So it divides the two terms, so it will divide the difference of them. So it'll divide B. So in particular, the greatest common divisor, it divides B. Okay. That's just what I've said in those two sentences. So that's the first direction of the equivalence. If there exists a solution, the consequence now is that D must divide B. Okay. So now we want to go in the other direction. Now we want to go in the other direction. So this time we're assuming that D divides B, and we want to find a solution now. Okay. So we're looking for, so what does that mean to find a solution? Well, we're trying to find an X which solves this congruence. So we're trying to identify at least one integer such that when you multiply it by A, you get something congruent to B. Well, again, that's going to involve messing around with equations involving A, B, and N. Okay? So you try, given the assumption you've made, you try and move from that assumption to some appropriate equation involving A, B, and N, and see if you can get that equation to tell you that A times something is indeed congruent to B. Okay? So that's the approach we take. So starting with our assumption that D divides B, well, if D divides B, you see again, you know, the starting off steps are often unraveling definitions in the assumption that you've made, or in the setup to the theorem, in the conditions given to you and stuff. So we're assuming D divides B, so that means we can write B as some multiple of D. I just called it B prime to indicate that it's related to B. So B is equal to B prime times D. Now D isn't just any old number. D is the greatest common divisor of A and N. I remember from what I've said before, I want to move towards an equation involving D, A, and B. So if D is the greatest common divisor of A and N, a key fact which comes from the Euclidean algorithm is that D is a linear combination of A and N. From the Euclidean algorithm, you can identify an integer R and an integer S that will give you this linear combination. Well, this is good because here I've got an equation involving D, A, and N. So I've got A and N involved in an equation now. I want to get B in there. And a nice efficient way to get B in there, because I know D divides B, and here I have the D sitting here. So I just multiplied the D by the appropriate thing to turn it into B. So I hit both sides of the equation with this B prime. And that kind of changes the D into B. Of course, it changes the coefficients in the linear combination, but it still preserves this thing as a linear combination of A and N. So that's good. So it keeps that structure. So now I've got a nice equation involving B, A, and N. So see if I can cajole this into telling me that there's a solution to the congruence AX congruent to B. Well, it's just a matter of moving some things around. I'm going to send the B over to the right-hand side and take the N over to the other side. Yeah, that's what I did. So you just rearrange this and you get A times whatever this number is minus B is equal to N times whatever that number is. Okay. Key thing that is, though, that these numbers inside these brackets are integers, very definitely integers, okay, because they're manufactured out of S and R and B prime, and those are all integers whose existence comes to us from either the assumptions we've made or the conditions in the statement of the theorem. But what am I looking at here? I'm looking at the difference between this multiple of A and B, and it's saying it's a multiple of N. So that means N divides this difference, which in turn means that these two things are congruent to each other. Okay? So going from just the equation involving integers, building up the definitions again, just to point out that this equation is telling us that A times this number is congruent to B. So that means there are solutions. Because look, there's a solution, R times B prime. Okay, R times B prime is a solution of the congruence. So I know that solutions exist. Now, it's by no means, this isn't telling us that this is the only solution. Where is the non-uniqueness? Where is the lack of uniqueness in that argument? There's no lack of uniqueness in B prime. B prime is simply the number B divided by D. So there's only one choice for B prime. But it's this R and S which come out of the Euclidean algorithm. Now, if you apply the Euclidean algorithm in a very prescriptive way, following the steps, because it's an algorithm, you will always arrive at the same coefficients R and S. But the coefficients R and S that you can find to give you this kind of linear combination equal to D, they're not unique. Okay? I think we proved that in one of the exercise problems, I think. So given any A and N, if you're looking for linear combinations of them equal to their greatest common divisor, there's an infinite number of choices of pairs of coefficients R and S. Okay, so that's where the ambiguity, or that's where the non-uniqueness comes in. And indeed, any choice of R and S will lead you to, well, it'll lead you to a different solution here. So every time you get a different R, you get a different integer R times B prime, which solves this. Okay. But it's not immediately apparent whether all these different choices R times B prime, whether they'll all be congruent to one another or not, or whether every choice of R will lead to a new distinct congruence class. Well, that can't be possible because there are only a finite number of congruence classes around anyway. And so there's only, at most, there's only a finite set of solutions, finite set of congruence classes that might be solutions to this. So, so that's that. So that result gives us this nice clear condition. D divides B. That condition, whether that's true or false, determines whether there are or are not solutions. Okay. But we can see here a method for obtaining a single solution, but it's also non-unique. There's any choice of R and S will give you a different integer solution, and it's not immediately apparent how these different integer solutions, whether they'll be congruent to one another or not, and how many different congruence classes you might see coming up. Okay, so that's what's that's what remains to be settled there in that question. Okay. I've maybe not left myself a huge amount of time. I think we'll have to consider this proof tomorrow, just before we look at the examples. So we'll do this proof tomorrow and then do the examples. But let's just take in the statement of it now. So this focuses on, so with the knowledge now from the previous result that in order to have solutions to AX congruent to B, you have to have D dividing B. So we assume that now. Suppose that there are solutions. Suppose that D does divide B. This result is describing exactly how many solutions there are and how to go about defining them. Okay? So it's claiming that there's exactly D solutions modulo n. So there's exactly D different congruence classes modulo n that are solutions. And it gives a recipe for obtaining them. These are the congruence classes modulo n of this set of integers. Now this set of integers is determined by, well, the n and d come from the statement of the problem, n and d. So they're determined by these two parameters, t and I. I is ranging from 0 to d minus 1. So that's the thing that's counting the solution. So for each choice of I, between 0 and d minus 1, you get a different number here. T is a single unique number, and that's the single unique solution of this congruence here. So you can see what we've done there. We've applied this theorem 4.4 here to just go to divide each part, or the theorem 4.3 really. Sorry, the theorem 4.3 we've divided the left-hand and right-hand side of the congruence by D, and so we must divide the modulus by D as well. So it's this reduced congruence, and because you've divided out the greatest common divisor of A and N, that means that now this new coefficient of X will actually be co-prime to this modulus here. Okay. So D is the greatest common divisor of A and N. So when you get rid of it from A and get rid of it from N, the bits that are left behind, A over D and N over D, they're going to now be co-prime to one another. So because they're co-prime to one another, there's a, no, it's not this, it's from on the previous page. Because they're co-prime to one another, there's a unique solution. So T is the unique solution of this congruence. Okay? So T is a unique number, and then I is this parameter which varies from 0 to D minus 1. And this theorem is claiming that each of these numbers represents a different congruence class, modulo n, which solves this linear congruence, AX being congruent to B. Okay, so you can have a read through the proof there before tomorrow. We'll go through it fairly quickly tomorrow, well, at an appropriate pace, and then we'll have a look at lots of those examples, and we'll introduce the next result, which is the Chinese remainder theorem. Okay.